Okay, welcome back to this lecture. Urysohn's embedding theorem. In previous lecture, we defined R infinity, which is the set of infinite tuples of real numbers, which are square summable. Or you can say R infinity, the set of square summable sequences, because these are actually sequences. Square summable means summation I runs from 1 to infinity mod of x square is finite. Okay. Now we define a metric on that. On this R infinity by d of x by equal to summation n runs from 1 to infinity mod of x n minus y n square whole power 1 by 2, where this x it is an infinite tuple x n, y is an infinite tuple y n. Then you can easily verify that using Minkowski's inequality, that this D is a metric on X, and this therefore R infinity is a matrix space, and in fact it's actually separable, because the set of infinite tuples of rational numbers, which are square summable, is a subset of R infinity, and which is also dense in R infinity under this metric. Okay, so though therefore it is a separable matrix space, and every separable matrix space is second countable. So thus R infinity is a second countable matrix space. And also we know that every subset of a second countable space is second countable. Therefore every subset of R infinity is also second countable. Okay, now let's define a meterizable topological space. A topological space x tau is meterizable if there exists a metric D on X such that the topology generated by D coincides with tau, the topology on X. That is, if tau dash is a class of open sets generated by the metric D, then this tau dash is also topology on X, and this tau dash is equal to tau, then we can say the topological space X tau is meterizable. Now we state Urysohn's embedding theorem. It states that if X is a normal space and second countable, if X is a normal space and second countable, then there exists a homomorphism f of X onto some subspace of R infinity. So X is normal space and it is also second countable. Then there exists homomorphism of X onto some subspace of R infinity. So that means this normal space, which is also second countable, can be embedded in some matrix space. So hence this X is meterizable. It means that this X is meterizable. So that means every topological space which is normal as well as second countable is meterizable. In general, every topological space is not meterizable because we have a topological space which are not Hausdorff spaces. There are some topological, it's already discussed in previous lectures. The topological space which is not Hausdorff cannot be meterizable because matrix space is always second countable. Matrix space is always matrix space is always a Hausdorff space. So that means a topological space which is not Hausdorff cannot be meterizable, or if it is meterizable then it should be Hausdorff. So there are these are the examples of topological space which are not meterizable. But here is a theorem which states that if a topological space is normal space and second countable, then it must be meterizable. Let's prove this theorem. So proof. First case, suppose this our topological space X is finite. Suppose it's finite. We need to show that this X is meterizable. Suppose X is finite, and let Y be subset of R infinity such that cardinality of X is same as cardinality of Y. Okay, since this X it's a normal space, therefore it is first a T1 space, and in T1 space every singleton set is closed. So since X is T1 space, and therefore every subset of X is closed, and hence hence every subset of X is open. If every subset is closed, then every subset is also open. Also, this Y is a subset of R infinity, and R infinity is a matrix space, therefore it's a T1 space, and Y is a subset of R infinity. Y is also a matrix space, therefore Y is also T1 space, and it is also finite because the cardinality of Y is same as cardinality of X. So Y is a finite and it is also T1 space, so that means every subset of Y is also closed. Also, every subset of Y is closed, so therefore every subset of Y is open. So thus both X and Y, they are actually discrete. As a topological space, they are actually discrete topological spaces because every subset of X is open, every subset of Y is open. Now their cardinality is same, therefore there is a bijection. So let F from X to Y be a bijection. Be a bijection. So this every map between X and Y is open because X is discrete topological space, Y is also discrete. So that means every map between X and Y must be continuous, because for continuity inverse image of open set must be open. That's so if you take any open set here, then its inverse image is a subset of Y, a subset of X, and every subset of X is open. So that means inverse image of any open set is open in X. So that means F is continuous. Then F is continuous. Then F is continuous. Also F inverse is continuous. Also F inverse from Y to X is continuous because Y is a discrete topological space. So inverse image of every open set in X is open in Y. Also F inverse is continuous. So thus F from X to Y is a subset of R infinity, is a homeomorphism. Is a homeomorphism. So therefore X is metrizable. Therefore X is metrizable. Because Y is matrix space and X is homeomorphic to Y, therefore X is also metrizable. Okay, so in this case we are done. So if X is finite, then X is metrizable. Then X is homeomorphic to some subspace of R infinity. So now we take if X is not finite. 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 X is not finite. Since this X is second countable, therefore it is a countable base. So since X is second countable, since X is second countable, therefore it has a countable base. It has a countable base. So let's take its countable base. Let G1, G2, so on up to infinity be a countable base. Be a countable base for X. Suppose it's a countable base for X. So we assume that each set in this countable base is whose each member is empty, whose each member is empty and non-empty. Sorry, whose each member is non-empty. Because if any member of this class is empty, then we remove that member from this class. Whose each member is non-empty and different from X. And different from X, because there is, if suppose there is X, then this singleton X is in. So we can choose an open base, countable open base, which doesn't contain x. Okay. So this each gi is different from x. Each gi is different from x. So we can assume this. We cannot lose anything by this assumption. Each member of this class is non-empty, and each member of this class is different from x. And these sets, the members of base are called basic open sets. So they are the basic open sets, and it's a countable base for x because x is second countable. So if we have any open set in this countable class, if gj, so let us denote this class by b belongs to b is an open base, and x belongs to gj, gg. Since our space is normal space, and by the lemma which we have proved in the previous lectures, where we have applied it in the Urysohn's lemma, that was the lemma 2 actually in that case, in that theorem. So by that lemma, given any open set G and given any point x in G, so given any neighborhood Gj of x, there exists a neighborhood Gi in B such that x belongs to Gi, subset of Gi closure and subset of Gg. Okay. So actually that lemma states that if x is that x is T1 in regular space, but every T1 in regular space is also a normal space. So that lemma states that if x is a normal space, then given any neighborhood u of x, there x is a neighborhood v of x such that x belongs to v, subset of v closure subset of u. But we can apply that lemma to these basic open sets also, because this Gj is an open set containing x, therefore it's a neighborhood of x. So there must exist some open set, say O, not necessarily Gi, say O, such that x belongs to O, subset of O closure subset of Gj, Gg. Since x belongs to O and this collection, it is an open base for x, therefore I can find some member, say Gi, in that class. So there is some Gi in this class B such that x belongs to Gi, subset of O. Because this collection, it is an open base for x, therefore for any open set O, I can find an open set in this collection, say Gi, such that x belongs to Gi, subset of O. So let's apply it here now. It means that x belongs to Gi. So it means that Gi closure is subset of O closure. Okay. So this means x belongs to O. It means that x belongs to also Gi. Gi is subset of O, and it's subset of Gi closure, which is subset of Gj. So that can be easily done. So we can choose a basic open set here actually. Lemma states that there exists an open set containing x with this property, but here we can choose basic open set because every open set is actually the union of basic open sets. Or for any open set O and a point x in O, we can find the basic open set Gi such that x belongs to Gi, subset of O. That can be done. So in this way, we have a collection of pairs, say Gi, Gj, satisfying this property, Gi closure is subset of G, J. So the set of ordered pairs, therefore the set of ordered pairs Gi, Gj with such that Gi closure is subset of Gj is countable. It's a countable collection because Gi's are countable, and let's denote this countable collection by the countable collection is a countable collection, and denote this countable. We can arrange this countable class and denote this collection of ordered pairs. This collection of ordered pairs by this P1, P2, capital P1, P2, Pn, and so on. So this collection of ordered pairs is countable because Gi's are countable, and let's denote this collection of ordered pairs by this Pn. So P1 is some ordered pair, P2 is some ordered pair, P3. So they are all Pn. They are all ordered pairs actually. P1 is some ordered pair, but this ordered pair has this property: Gi closure is subset of G. So let's take this. Let Pn be the ordered pair Gi, Gj. Then this Gi closure is subset of Gj. That's the definition of this pair Gi, Gj. So which also implies that Gi closure is subset of Gj. It's a Gi closure. It is subset of Gj. It means that Gj complement is disjoint from Gi closure. So this means that Gi closure intersection Gj complement is the empty set. So that means Gi closure and Gj complement are disjoint closure subsets of X. They are disjoint, and because Gj is open, therefore its complement is closure, and therefore its complement is closed, and closure of every set is closed. So they are closed sets and they are also disjoint. They are disjoint. Now we apply Urysohn's lemma. By Urysohn's lemma, because X is an orbital space, by Urysohn's lemma, there exists a continuous map for this pair. There exists a continuous map. Let us denote that continuous map by Fn from X to say interval 0, 1, such that it maps this closure set Gi closure onto 0. Gi closure is equal to 0, and it maps the second closure set Gj complement onto 1. That's by Urysohn's lemma. Now for each, actually we need to define a map from X to R infinity. So let's define that map now. So now define F on X by F of X is equal to F of X is equal to Fnx. Fnx is a real number lying between 0 and 1. F2x divided by 2. F3x divided by 3. Fnx divided by n, and so on and so forth. So it's an infinite tuple of real numbers because it's, F1x is a real number, F2x is a real number, F2x by 2 is a real number, F3x by 3, because Fn, it's a what's Fn actually? Fn is a function. Here you can see Fn is a function. Fn is a function from x to 0 to 1. So So image of each point is a real number lying in the interval 0 to 1. So they are actually real numbers. So it is an infinite tuple of real numbers. Now we will show that this infinite tuple, it belongs to R infinity. So that will give f is a function from x to R infinity. So now let's check this. Let's check this summation. Sum of scales, okay? Let's check summation f and x divided by n and runs from 1 to infinity. It is square. So, but each f and x is less or equal to, it's less or equal to summation n runs from 1 to infinity 1 by n square. That's finite. The reason is mod of f and x is less or equal to 1 because f and x is a function from x to 0 to 1, interval 0 to 1. So therefore f of x belongs to R infinity for all x belongs to x. So thus f is a function from x to R infinity. So this is the function that we show that this function is it's 1 1 and it's also continuous, and the inverse map is also continuous. So this will give that this x is embedded in R infinity. So we need to show that this f is homeomorphism from x to f of x actually. So let's prove that okay. So first we show that now it's now we show that f is 1 1, f is continuous, and f inverse from f of x to x is continuous. We need to show that these three properties for f. Okay, so first we prove f is 1 1, that's trivial. First property, f is 1 1. So it's an exercise for you. F is 1 1. Now I prove second that f is continuous. F is continuous. So let's prove this continuity of f. So what's f? F is a function from a topological space x to